Hi, myself Venkateshwarlu, a PhD student working with Professor Ram Prakash Bharti at the Department of Chemical Engineering, IIT Roorkee. I thank the American Chemical Society for giving me this wonderful opportunity to present my research work. I will be talking on effect of surface wettability on droplet formation in a cross-flow microfluidic system. These are the contents of my presentation. During the pandemic, it is very important to get the medical reports of the SARS-CoV-2 virus in time, and there are many challenges associated there. Fundamentally, applications like this involve the hydrodynamics of droplet generation in a microfluidic device. For instance, the figure shows lab-on-a-chip device consists of a genosensor for the detection of SARS-CoV-2 virus by analyzing the generated droplets herein. One of the key parameters that determines the evolution of the droplet shape and size is the surface wettability. The surface wettability is essentially the reciprocal of the contact angle. It represents the the strength of the fluid-solid interaction. Hence, the present study has aimed to focus uh, to investigate the effect of surface wettability on droplet formation in a cross-flow microfluidic system. Consider the two-dimensional laminar cross-flow of two fluids through T-junction rectangular microfluidic device. The T-junction is constructed by a vertical channel intersecting perpendicular to the horizontal channel. The blue color represents the continuous phase and the red color represents dispersed phase. The present physical model can mathematically be expressed by the conservation of mass and momentum equations. Since there is an interface exists between two phases, and that would require an additional equation to track the topological changes of the interface. Hence, the conservative level set method has been adopted to track the interface movements. The level set variable phi ranges from 0 to 0.5 for the continuous phase and 0.5 to 1 for the dispersed phase. At the interface, phi value is equal to 0.5. The assumptions, both the fluids are assumed to be equal in density, Newtonian, immiscible, and incompressible. The interplay of the forces responsible for the droplet breakup is explained in terms of capillary number and Reynolds number. Capillary number is defined as the ratio of viscous force to the surface tension force, and Reynolds number, inertial force to the viscous force. The governing equations are constrained to the boundary conditions as mentioned here. The pure fluid phases, that is level set variable phi equal to 0 for the continuous phase and 1 for the dispersed phase, are entered through the respective inlets of the channels during the simulations. Constant flow rates QC and QD are imposed at the inlets. The outlet is open to the ambient and the channel valves are taken to solid. That is, the no slip boundary condition is imposed. The numerical parameters and details regarding the mesh independent study are provided here. The mathematical model has been solved using the finite element method based COMSOL multiphysics. The two-dimensional mathematical model is chosen from the COMSOL multiphysics software as microfluidics, multiphase flow, two-phase flow, level set laminar flow modules. The computational domain described as a linear, non-uniform, triangular, and structured mesh. The finite element method is used to transform the transient partial differential equations into ordinary differential equations. Then finally, the discretized equations are solved by a fully coupled Pardiso and Newtonian's nonlinear solvers. The numerical solutions are performed with the optimized geometrical parameters from the mesh independent study as shown over here is optimized that non-uniform triangular mesh consisting of 13,766 elements with a maximum element size of 10 microns is sufficient to perform the simulations. The present results have been validated with the experimental and numerical results of the results for the effective droplet diameter and length over the wide range of QC, QD, and QR. For instance, first case, QC, the flow rate of the continuous phase, is varied by keeping QD, that is flow rate of the dispersed phase, constant. Second case, QD is varied by keeping QC constant. And third case, QR is varied, that is flow rate ratio, the ratio of flow rate of the dispersed phase to the flow rate of the continuous phase. The length of the droplet is measured by plotting the level set variable along the length of the channel. The effective droplet diameter is determined by using the following relation as shown here. The variation of the effective droplet diameter length are seen to be consistent and have shown satisfactory agreement with both experimental and numerical results of the literature, and thereby establishing the accuracy of the present modeling and simulation approaches. The instantaneous phase profiles of the invisible phases during the droplet formation are shown over here. The formation of the droplet is classified into various stages. In the initial stage, the dispersed phase enters through the vertical channel into the from the vertical channel into the main channel. In the second stage, the dispersed phase opposes the flow of the continuous phase and hence causes the pressure rise in the continuous phase upstream. When the pressure in the upstream of the continuous phase is sufficiently large enough, it starts exerting shear on the dispersed phase and eventually collapses the interface. On moving further, after detachment, the dispersed phase splits into two separate domains. It is observed that at lower values of theta, that is contact angle, for hydrophilic conditions, the dispersed phase is completely wetting the channel walls. Hence, there is no clear droplet formation. On increasing the contact angle little bit, the dispersed phase has shown less contact with the walls and consequently attains a concave shape with sharp edges as shown over here. For the hydrophobic conditions, that is when the contact angle is above 90 degrees, the dispersed phase is forming a clear droplet with a minimum contact and try to escape from the wall. For super hydrophobic condition, that is when the contact angle is above 150 degrees, the dispersed phase has negligible contact with the walls. Thus, the droplet being formed is a round, clear, and monodispersed. The effect of contact angle and capillary number on droplet formation time and droplet size is discussed here. It is observed that the droplet length is decreasing with an increasing in the capillary number of the continuous phase. However, the droplet size is increasing with the increase in the contact angle for the same conditions. For low values of contact angle, that is for hydrophilic conditions, the length of the droplet is randomly changing as it is having more contact with the solid walls. And the surface, the curvature is attaining a concave shape with sharp edges as discussed in the previous slide. However, the droplet is attaining a smooth shape for the hydrophobic conditions as the curvature changes from the concave to convex. The droplet formation time is decreasing with increase in the capillary number of the continuous phase, and it is smooth for the superhydrophobic conditions. The evolution of the pressure profile in the continuous phase, dispersed phase, and downstream of the main channel are shown here. The locations at which the pressure is recorded are A, B, C. A is for continuous phase, and B is for the dispersed phase, and C is in the downstream. The pressure in the upstream of the continuous phase is responsible for the droplet pinch off or breakup. The developed pressure in the upstream starts forcing the dispersed phase toward the outlet after the dispersed phase occupies the whole width of the main channel. The local pressure fluctuations for hydrophilicity are shown here. The fluctuations are insensitive in the continuous phase for theta equal to 30 degrees and slowly increasing for 45 and 60 degrees. Hence, the dispersed phase is in more contact with the wall and unable to attain a precise shape to form a droplet. However, when the contact angle is 90 degrees, there is a droplet formation. Droplet formation as the dispersed phase repels from the solid wall. During the initial stage, a gradual rise in the pressure is followed by a sudden shoot up when the dispersed phase fills the channel, thereby restricting the continuous phase flow. In the final stage, the developed pressure in the upstream of the continuous phase breaks the interface and forms two separate dispersed phase domains. Similarly, the sensitivity of the pressure fluctuations to hydrophobicity is presented here. In the continuous phase of the main channel upstream, the pressure fluctuations remain same in the entering stage for all the values of theta. However, the dispersed phase experiencing the shear from the surrounding fluid once it restricts the flow of the continuous phase. Thereby, the pressure developed in the upstream of the channel. It is also observed that the maximum value of the pressure is obtained for the superhydrophobic conditions. That is, when the contact angle is above 150 degrees. After the hydrodynamic development, the process of droplet formation repeats and becomes a cyclic. The fluctuations of the pressure in dispersed phase, that is at location B, are shown here. However, the fluctuations are in opposite or antiphase with the continuous phase on the upstream. These two are PA and PB are in antiphase with each other. And it is noticeable for when theta, the pressure fluctuations in the downstream are negligible. In summary, the droplet hydrodynamics, droplet hydrodynamics is strongly dependent on the set of operating conditions, especially the contact angle. The pressure history can efficiently be utilized for the suitable design and development of the microfluidic device for the on-demand droplet generation. In conclusion, the present study of the droplet formation in a T-junction microfluidic device system has provided new insights. The droplet behavior has been studied for a wide range of capillary number and contact angle. For the hydrophilic condition, the curvature is adopting a concave shape, and thus the droplet length is not uniform. The droplets are monodispersed at low capillary numbers for the hydrophobic condition, and other things are evolution of the pressure profile has been discussed to explain the droplet breakup mechanism. These new insights help to design a suitable microfluidic device to ease the control of the contact angle based droplet production. I'd like to acknowledge the support of the Department of Chemical Engineering, IIT Roorkee, and the Ministry of Education, Government of India. Thank you for your patient listening. If we have any questions, then feel free to